So on. And then if I were to sketch a horizontal line. From the horizontal to here, this is our okay. And the slope when it's anti-clockwise is positive. When it's going clockwise, the slope is negative. Okay, so for this case, we have it as anti-clockwise. So if we will pick another point down here, right? So if we were to draw a tangent, right? If we were to draw a tangent, so if I were to sketch a horizontal line, now, right, you can see it's different direction. So this is a negative theta, right? It's going in a clockwise direction, okay? So now, at x is equal to 0, do we know the slope? We have not a clue what is the slope, okay? And when at point B, when x is equal to L, we also don't know what's the slope. So we don't know what is this gradient that I'm going to sketch in green. Okay, we have not a clue what is this gradient. Okay, we don't know what is this gradient. Likewise, we also don't know what is this gradient over here. So we don't know. But one thing we know for sure, okay, y is equal to 0 because at x is equal to 0, y is equal to 0. When x is equal to L, y is equal to 0. So with this, how many boundary conditions do we know? We know boundary condition number 1, boundary condition number 2, boundary condition number 3, and boundary condition number 4. So simply supported is one of the most commonly known structure. Okay. So the next one that we're going to look at is we are going to look at a cantilever beam, which is also very commonly observed. Okay. So the next one we have a cantilever beam, or sometimes is known as a built-in. Okay, sometimes you see the word built-in. So how does this actually look like? Okay, so this will have it will have a wall. Okay, and the beam is built into the wall. It's built into the wall. So at this point down here, x is equal to 0, and the point down here, x is equal to L. Okay, so we will have a load at point P. Okay, and you can also have an evenly distributed load in between somewhere around here, for example. Okay, so again, we will write down our boundary conditions. So we will have our B, M, theta, Y. V, M, theta, Y. Now, these boundary conditions are important, okay? Don't memorize them. More important is the ability to what? Visualize them, okay? Okay, so if I were to draw our reaction force, and I will call this at point A, and I will call this at point B, we know that, and this is our transformation, this is our X, and this is our Y, okay? So what we have over here, right, at point A, we will have a AY, and we also have a moment at point A. The moment at point A is going in a anti-clockwise direction, right? Because the moment at point B, this is the moment due to what? Due to P, right? So it has to counter, okay? So now, how will our structure deform? Now, I want you to watch how I draw the deformation. Okay? And I want you to, so when it's built in, usually you have zero slope. Okay, I'm going to draw literally draw a very small straight line. Okay, we're going to have a very small straight line. Sorry, bad idea. I'm going to draw a very short straight line. And then it's going to bend this way. Hey, hey. Okay, so this is the deformation pattern. Okay. So when x is equal to 0, what is the shear force or what is V? We don't know. But when x is equal to L, we know that this is equal to what? 0. Okay. When the next thing is moment, when x is equal to 0, the moment is, we don't know what is the moment because we have moment at point A. But when x is equal to L, the moment is equal to 0. Okay. And then the next thing is the slope at x equal to 0, theta is equal to 0. When x is equal to L, we don't know. And the last one is straightforward. Deflection is equal to 0. This we don't know. Okay. So for built-in, an important thing to note for built-in, right? Theta is equal to 0 at the built-in end. Okay. What I'll do, I'll bring a camera next week and I'll show you by bending the ruler. Some of you have seen it before, and you can see that the slope is indeed equal to 0. So now if I were to zoom outwards, or now how many boundary conditions we have? Okay, so we have boundary condition number 1, boundary condition number 2, boundary condition number 3, boundary condition number 4. Okay, so now if I were to zoom out, okay, and you can see the top structure is simply supported, and you can see the boundary condition for simply supported beam and the cantilever beam are not the same. Okay, for the boundary condition. Now, the third structure, the third support that is very commonly observed also is what we call the overhanging beam. Okay, so for the overhanging beam, so this is our point A. And over here, we have a roller, our point B, then our point C. Okay. So we can have any types of load. So maybe down here we have 2 different loads. Okay. And over here we have a simply supported or evenly distributed load. Okay. So now we call this X is equal to 0, X is equal to L, and here X is equal to 3L over 2. Okay, so if I were to specify our distance, this is our L. And then from here to here is our L over 2. Okay, so the next thing we're going to do is V M theta Y. B M theta Y, and then we also have B M theta Y. Okay. So at x is equal to 0, we don't know. We know that AY has a reaction. We don't know why is it. At point B, we don't know. At point C, we also don't know. Okay. Now for the next one, the moment at point A is equal to what? So if you remove the support at B, this will be equal to what? 0, because the whole thing will roll down. However, we have to be very careful over here. When x is equal to L, moment is not equal to 0. Why? Because you have some moment acting in this direction and another moment due to the distributed load acting on the other direction. So m is not equal to 0. However, when x is equal to 3L over 2, this is equal to 0. Okay. So the next case, the boundary condition, the slope we don't know, or the slope we have not a clue, but y we know we have one y here. X, when x is equal to 0, y is equal to 0. When x is equal to L, y is equal to 0. Okay. So for this case, again, we know boundary condition number 1, boundary condition number 2, boundary condition number 3, and we know boundary condition number 4. Okay. Now overhanging beam is more slightly more not complicated, but slightly we need to solve in what is it? We need to create extra boundary condition, which I'll show you later. Okay. So now these are the most important thing is these are the most commonly supported structure, which is simply supported. You have cantilever beam and we have overhanging beam. But more important is when moment is equal to 0 and when moment is not equal to 0, and in what condition is a shear force equal to 0. Boundary condition is a key. In buckling, you have to be able to identify boundary condition. If we cannot identify boundary condition, game over. Okay, so in buckling, you have to know how to what? Identify boundary condition. Okay, so now all of you should know boundary condition. Okay, so we are going to do a cantilever beam next, example of cantilever beam. Okay, so in a cantilever beam, what we're going to do, so we have a beam now. And the beam is built in. Okay, the beam is built in. And the beam is under a gradient distributed load. Okay. So over here, this is our omega naught. Okay. And then we have our point A. We have our point B. And then we have our, over here, from here to here, we have our length. Okay. So what I propose, we take a 10 minutes break. We come back at 8:50 and we start on this example. Okay. I'll see you all later.